Hello guys, and welcome back to my channel Civil Construction and Tutor, and in this video we'll be modeling and analyzing a steel connection between steel column and base plate which will be connected on the pedestal. For designing this, we'll consider the base reaction from ETABS and we'll consider the envelope load combination to take the maximum value. So basically envelope comprises of all the steel load combination and will give the maximum or minimum as per our requirement. So for designing the base plate, we'll consider moment about x and y and axial force Fz. So you can take either the maximum or minimum and we'll consider that. So for defining the area, or we are required with the maximum compressive force, and for the bolt, that is pull out force, we'll consider the minimum, that is the upward pulling force. So due to its higher value of dead load, we don't have negative Fz, that is pulling force. It is all downward force. So in such cases we may not require anchor bolts. So we'll check that. So for this I'll be using Idea Statica for the connection design, and here you have the base plate connection. So by default you can get this type of connection here. This is the shear connection and this is the bolt connection, moment connection. So in the shear connection you can see that the anchor bolts are within the wave or near to the wave, and as we know, for the I-beam the flanges are responsible for carrying the moment while the wave is responsible for carrying the shear force. And in the moment connection you can see that the anchor bolts are spaced near to the or placed near to the flange. So here you can see the moment connection also comes with stiffener. So what is the role of this stiffeners? We have to understand that. So we'll consider this type of connection and we'll check whether we'll require stiffener or not. Here we have a built up column. So firstly we have to model a built up column in Idea Statica as well, and it will rest on a column pedestal. Firstly let us add cross section, that is built up cross section. So for this go to add new. In the welded and composed, here you have general steel connect cross section steel. So we'll model, and we have a built up column made up of two channel sections. So consider channel section, and we are considering ISMC 200. So ISMC 200, okay. Edge distance, that is D, for the built up column is 200, that is 100 mm from the origin on either side. So I have already shown that in one of my video of column beam connection, you can find that. So I'll directly use that value here. So this is Y and Z, so I have to provide offset in the Y direction. Let me add a copy of this, and that will be mirror 78. So to check whether the distance is 200 mm or not, I'll simply add a plate, that is the batten plate of this is the plate of width 200 mm and check whether it is okay. So you can see 200 mm and it will be provided in this particular face. So $200 that means this is 200, so it will be 100, and considering the thickness as, so what are the 10 mm, so I'll provide 8 mm and it should be 160 mm considering freeboard on either side to provide weld. So I provided 200 mm just to check whether the spacing is 200 or not. So Z I'll provide 100 and 8 mm thickness, so center to center it will be 104. Similarly I'll add a copy of this on the other side and it will be minus 104. So in this way you can model built up column in IDEA Statica. Okay. So the geometrical type will be ended. If you keep continuous, it will show an error because for the base plate it should be ended type. And we have a fixed type connection, that is moment type connection. So n vy, vz, mx, my and mz. So this is the model type. Then we have load effects le1. So we have to assign the load. So we'll consider the axial load and the moment on either side, that is my and mz. So keep the local axis on and you can simply understand this. So it is little bit different from the ETABS because we had x, y and z. So now let us see the load from ETABS. So let us go, okay, firstly keep this as standard graphics, okay, and go to plan for the base and we'll see the reaction tabulated. Maximum. So I think this is the maximum one, 284. So axial force 284 and that should be negative considering the local axis x upward. So minus 284 will give us the downward value. And similarly we'll consider my and mz, which is mx and my in ETABS. So 38, 33, 41, 31. So we'll consider the maximum value 47, 38. So 50 and 40 shall be sufficient. Okay. Now base plate. So the member that is connected to it, it is column. Okay. Material of base plate Fe250 is also okay. Thickness 20 mm, that is also okay. Generally we use 20 mm. Dimension, so let me go into the plan. To profile symmetrical rectangle you can have. So for now let us keep this as rectangle. So you can find this all dimensions. So top it is 120, left 80, bottom 100, right 50. So we have 200 overall length, 200 mm on either side. So we have to keep this with respect to end distance of the bolt. So top 120. So let us keep this as 75 for now. 75, 75 and 75. So we'll get a square base plate. Anchor. So if you want to keep anchor bolts, then we have to consider that as well. So for now we'll keep low grade bolts M20 of 4.8 grade. Anchoring length let us keep as 300 mm. So anchor type, this is about the end. So for now it is straight. You can also have a circular washer plate at the bottom or a square type or rectangular type. So generally we'll keep this as straight. Shear plane in thread, we'll consider this. So if we consider shear plane in thread, we are actually reducing the shear capacity of the bolt, so that will be in the safer side. We have this connection, flanges and web. So it is not possible to provide double fillet weld, so we'll consider a single on the rear side of the flange, and for the web also we'll consider the rear side. Now foundation block. So for now let us assume M20 concrete pedestal and offset of 300 mm. So you can see this is the offset. So 50 mm offset we'll consider, and depth 600 mm, or we can even go for 1000 mm offset. Generally we'll consider 1000 mm offset, and that will directly rest on the foundation. Shear force transfer from friction, that is also okay. Now we'll check for the anchor. So right click, editor, and here you have the bolt, explode. So now you will edit this. And what was the dimension of the base plate? So 75 to 16 and 75. We get this as 366. So let us make this as 360. So 3 mm on either side. 72, 72, 72, and 72. So this becomes 360. Now let us edit. So the value is 360 for now. Explode from the origin, and here we'll add 4 bolts. So we have to know the coordinates. So we are using 16 mm bolt, so the end distance should be 1.5 times of nominal size of diameter, so that becomes 24. 1.5 times into 16, so 360, that means 180. 180 minus 25, we get this value as 155. So let us keep this as 155. 150. Okay, for now we'll keep 140, not as 25. So 140, then we'll get 140, and this also 140. We'll copy this. Now the second will be over here, that is negative x. Add a copy of this, so all of them will be minus 140, minus 140, and the last one will be 140 and negative y. One 40 minus 140 minus 140 minus 140 minus 1 2 3 4 bolts. Apply. Okay, so we got the connection. Now let us calculate whether the connection is sufficient or not. So the weld size is not sufficient, and the concrete block is also not sufficient, so we have to revise these things. So for this we'll increase the size of weld, so let us provide 8 mm weld, 8 mm weld, and concrete. Either we can increase the base plate. Considering the effect of moment, as I already said, the moment is transferred in form of tensile and compressive force on either flanges, so we have to consider that effect as well. So let us increase the dimension. So let us keep this as, and we have also increased the thickness of weld. Now let us calculate. So here you can see the weld and concrete block is still not satisfied. Now let us try to add stiffening members. So now let us add the stiffening member here. So that will be a rib, you can see here. So you can see here. Now let us make that as 75 and this as 100, and you can see here it is being connected on either side, that is due to surface both. So keep this as upper or either lower, so that will be lower, and it will be the at the center, so it is okay. And let us use a thickness of 5 mm. Now let us add this to this wave, that will be wave 2, and the surface will be upper. We'll add on the flanges as well, so add a copy of this, and it should be top flange 1, and now we'll provide a offset position x. So let us try minus 35. Okay, or we can just do minus 20 and add a copy on the other side. So flange will be much more critical, so we'll add top flange 2, lower. Let's add this. So how does this stiffener works? That is the question that we have to address. So let us uncheck these stiffeners. So this will be the effective length or effective area, say. So this is the effective area of the base plate, and the base plate is designed considering this as a length fixed at one side, and the moment or load coming gives a moment at this end, and this is how the thickness of the base plate is governed. So this is a cantilever side, this is also a cantilever side, this is also a cantilever side. So this is the effective length. So with this we are calculating the thickness of plate required. Now if I provide a stiffener, for example over here, now you can see that it is divided into a number of members. For example, let us take this. Okay, so now it is fixed at this side, this is fixed at this side due to stiffeners, and we know the load transfer mechanism for this type of slabs. So it will be something like this. So the triangular portion over here will be taken by this, the triangular portion will be taken by this, the triangular portion, this will be resisted or transferred to this stiffeners. The only portion remaining, this is the free end. So what we actually did, we reduced the, so previously the fixed end was this, but now the fixity will come at this point. So this is the general idea, that is we are reducing the effective length with the inclusion of stiffeners. The previous effective length was this, now with the inclusion of the stiffeners, this moment is considered, this load is already transferred or is taken by this stiffener, this is being taken by this portion, and this portion is being transferred or carried by this stiffener. So only this portion is to be taken or designed or considered by the base plate. So this is how we can reduce the base plate thickness by adding the stiffeners. That is why stiffeners are used in the moment connection or fixed connection. Now let's calculate. So we can see that the connection is now done. So here you can see the analysis is performed 100% and all the members are within the permissible range. So in this way we can design the base plate. Now you can simply prepare the report. So the steel grade is Fe250, concrete grade is M20, and these are the arrangement of the column and the base plate. So foundation block of 460 by 476, depth 1000 mm. You can simply consider all these, and we have this value within the permissible range, so it is okay. These are the weld thickness that has been considered. And here you can see the deformed shape also, so you can understand that from the deformed shape. Let me show you. So one of the flange undergoes compression and another flange goes tension to resist this moment. So that is why flanges are held in position with respect to weld and bolt. That is, the flanges must be held in position by the provision of weld and bolts. So this is how the moment is transferred in fixed base. So in this way the base plate connection is designed, and we have designed this pedestal as well. So let us model that in ETABS. So we can find the size of the pedestal from the report. So 460 by 476. You can also find that from the plan view also. So just add all this, you will get. Come to ETABS, in the 3D view, uncheck this. Before that, let us define a model. So add new property, concrete, pedestal 480 by 480. Let us make a square pedestal. M20 480 by 480, column, and it should be HISD 500. Eight mm stirrup, 12, and corner bar 16. Considering NBC 105 2020, it will be 0.7 and shear will be 0.4. Okay. Now let us select all this, and here you have extrude, joins to frame in Z direction. So -1 meter and 1, apply. So these all are column pedestal. So assign frame, pedestal 480 by 480. Remove the fixity at assign restraints none, assign fixed. Now extruded view, so this is how it will be constructed in site. Now let us run the analysis. Now viewer revise preferences, design code IS456, okay. Perform the concrete frame design. So 1843, so all of them have 1843. That means it is the nominal reinforcement, that is minimum reinforcement. You can see 0.8%, that is the minimum reinforcement in column. Okay, so for 1843 you can consider 4 numbers of 20 mm bar and 4 numbers of 16 mm bar. That will give 4 into 16 mm bar, that means 201, plus 4 into 314 for 20 mm bar. So overall you will get 800 for 2060. So which is greater than 1843. So 4 numbers of 20 mm bar and 4 numbers of 16 mm bar. So in this way we can design column pedestal, base plate for the steel structure. I hope this video series helped you, and if it did help, do like this video, comment on this video, and subscribe our channel. For the foundation design, I have already uploaded a video. You can find this in the description. So I have already shown how to design isolated footing, combined footing, wrap footing, strap footing. So whatever the footing required, you can design as per the instruction that I have given in that particular video. I hope this video helped you, and if it did help, do like this video and comment and subscribe our